With the background of the exceptions now, what we are going to do is take a look at the section 4.1 of the document, and that kind of talks about the special registers. Now, as you can see, special registers are, well, only few, but we also need to then recall now that our processor could operate or had this execution level of 0, 1, 2, and 3. And some of these registers are going to be available only in EL1, EL2, and EL3. And they can actually have a separate copy in each EL. So on the right now are those details, but let me quickly tell you what are the registers, that we would have. So, well, across the different ELs, we only have like one copy of the 0 register and the program counter, right? And the stack pointer that is currently active can be of 4 different types, right? So each EL has kind of, its own stack pointer. And why would that be? It's because you want to isolate one execution layer from another, and so you would want to keep their stacks separate, right? So let's say an app crashed because the stack overflow happened. Then the question is, when you transfer the control to handle that exception, to handle that crash to the operating system. So, okay, let's say the app was running here using, SPEL0, stack pointer for the EL0. And let's say, it ran out of the stack space. So an exception would happen that the operating system running in EL1 needs to handle. But then to be able to do anything, the operating system also needs a stack. And that stack will usually be, the memory region that is pointed to by the SPEL1, right? And similarly, there is SPEL2, there is SPEL3. Now, again, if the idea of stack pointer is clear, then know that EL0, we do not handle any exception here. We handle none of them. So we only handle it in the, underlying or the higher ELs. Now then the question is, to be able to save the processor state, those kind of when an exception happens, we were wanting to save the processor state, the information about what the CPU was doing. And then we reasoned that the program counter and the P state would be like the right registers to capture the information about like immediately. And there is more that happens, but the software can take care of taking care like saving the GPRs, right? If those are also to be saved, but which instruction to go back and execute after the exception, and what was the state of the CPU when the exception happens or happened, that needs to be still preserved and saved. So for that, each EL starting from EL1 up to EL3 has this SPSR, saved program status register, and the ELR, exception link register. And exception link register then ends up saving the PC value, so it remembers what point to go back and start executing the normal program's instructions, and the P state is saved into SPSR, right? And so this becomes even kind of more evident, or this becomes more clear once we go to let's say the exceptions section, which is 10.1, and then there is this wonderful diagram here which is explaining that a program was executing in EL0, some exception happened here. So note how the program counter value was put into the ELR, exception link register, and the program status was loaded into SPSR of the EL1. Again, the exception happened in EL0, so the control is passed to EL1 in this case, right? And so this is saved, and now the exception is being handled in EL1. Let's say when we now exception handling is over. So in an attempt to return back to this location, what the CPU does is it restores back the value from ELR EL1 to the program counter, and then restores back the SPSR EL1 back to the P state, right? And in between, somewhere here and somewhere here, there can be store GPR. Like you can, like in the handler itself, the handler can make sure that the registers that it's going to touch and use for computation, it can save the registers of the program elsewhere, typically on a stack, then corrupt the GPRs, and while exiting it can restore back. Right. So at this point you have at this point you have the same state of the CPU as it was before the exception happened. One other thing is always the program counter is pointing to the next instruction, right? So let's say we had, for example, 4 instructions and the CPU was executing instruction 2, then PC or program counter would be pointing to, the next instruction. And so what happens is when we save this in the ELR, right? So ELR will equal to 3. When we return back, we say, hey, PC was pointing to 3. And so start fetching instruction from there. That's one other important thing. All right, so with this then, we are pretty much, done with the registers that you should be remembering. And let's just quickly go back and talk about those. So 0 register, program counter, stack pointer, and then program status register, SPSR, and ELR for exception related things. And then as we move forward, there is our P state register. Somewhere it should be, yes, there is P state register, and then the 32 or 31 general purpose registers. So if you happen to know this much, you can pretty much be useful on a team that is working with the A-class CPU, and kind of also be able to discuss with them and find out more information. All right, so next what we do is we dive into a case study where I walk you through some boot up code and then kind of show as to what all is happening and how the CPU state is changing.